All right, so we want to make a bodyplot. Well, so since we just did a Fourier transform, let's do a Fourier transform, and we'll do a bodyplot with that. And I'll show you kind of some special cool things with Fourier transforms. Okay, so I'm going to this is my program. I'm going to include this so that you can download it and take a look at it. It's called bodeplot01. And I'm going to run down to here. So the first thing I do is I'm going to set the sample frequency to 20 kilohertz. And so the sample period then is just 1 over the sample frequency. And then the number of samples I'm going to set to 2 to the power 14. If you have trouble running this, you can make this a smaller number. But you might as well make it a power of 2 because if you dive into the guts of how a fast Fourier transform works, what you'll find is that it always works on powers of 2. If you have, this is 16384. If you have 16385, then it's going to use an FFT that's 32,000. It's just going to pad it with zeros. And then the sample length, so the sample period divided by the number of samples gives me the sample length. So this is going to be 0.8 seconds long, and the difference between the frequencies is going to be the sample frequency divided by the number of samples. So that's all stuff that you did before, and so you can see that I'm going to get samples 1.2 hertz apart. And then so let me just go ahead and run this guy. Okay, so now I'm going to calculate the index just from 0 to 16383. And then I'm going to calculate the frequencies as just the index times the frequency. Now I like to keep things in columns. The reason I like to keep things in columns is because when I do that, I can see more of it. Plus, the MATLAB plotting functions are naturally column-based. If you have 2 big long row vectors, it'll plot them just fine. But if you have 4 or 5 plots, you can put them in columns, and it'll plot those. And so this takes care of the folding frequency, right? As as you just did, the frequency is a little odd. So let me go ahead and run that piece. By the way, these are cells, and if you hit a particular cell, if you just hit Control Enter, it'll run that cell for you. So now you can see that the frequency it goes from minus 1 e to the 4th to 1 e to the 4th. There's a little bit of an index issue there. That's why that says 1, but we'll get rid of that here in a minute. So now I want to calculate the time. Okay, so this is the sample period, and so this is just the time vector. And I put this in here, so if this is true, then I'm just going to generate random numbers. But I wanted to be able to check to make sure that I had the frequencies right, because that can be a little bit tricky sorting those out. So I can either generate a random sample, which is what I'm going to do this time, or I could generate a cosine of 100 hertz. So we'll do it both ways so you can see. So I'm going to execute that one. So next I want to take the FFT. Now, and you see, so it's a complex number, right? So there's the samples, and there's the complex numbers. And then I'm going to plot it. And so you can see here that this is actually a uniform spectrum. I mean, it doesn't really look that way, but it is. And if you take a random sample, you get a uniform spectrum, and you get arbitrary angles. And so now, so now if I take that and I filter it, and so this is a first order filter at 100 hertz. So I'm going to filter it, and you can see how I did this. This is I just went through the samples, and I took the old output and multiply it by this guy K, which I'm not going to explain how you do that, but that's how you find a filter constant. And then I take the actual sample times K. So I use a whole lot of the old output value and a little bit of the new input value. And I do that every time as I go through and step through the epochs. and it's a filter. And so now I'm gonna take the FFT of the filtered response and I'm going to plot it. Okay. So there is the oops. So there is the frequency response. And of course, this doesn't really look like a bodyplot because it's got both plus and minus frequencies. So let's turn that into a bodyplot. And there you go. And so let's look and see how I did the bodyplot. Well, so first of all, I just took the positive frequencies, and then there was that one oddball, so I got rid of him. And then I take the I set the magnitude is equal to the filter magnitude divided by the maximum of the filter magnitude. I take the log 10 of that times 20, and that's what I plot. Now, there's another way to do that, and that's I can so this is what I got. So the blue line is what I got from the FFT. But there's another way I can do it. I can just I can plot a bodyplot, and this is how I would do a bodyplot. So I take tau, which is the radian frequency at which that breakpoint is at, times s. It's the time constant, so it's 1 over the frequency, multiplied by s minus 1. And so this is 1 over tau s plus 1. And that's a S-domain transfer function. And so if I take the magnitude of that guy, just calculate him, so it's a bunch of complex numbers, and then take 20 times the log 10 of that, and I plot it, then this is what you get. Right. So the blue line is what I got from the spectrum, and the red dotted line is what I get from the actual calculation. And the reason this curve doesn't match quite right there is because you get into some aliasing effects. All right. So now I want to do it from scratch. And so this is where you should probably start paying attention, because from line 78 here, where I said now do the bodyplot from scratch, I'm actually going to do all of this and plot the bodyplot. So I need a start frequency, and so my start frequency is going to be a 10 to the power 0 in this case. Although when you do your plot, you might want to go from -2, and F1 is going to be the ending frequency, which is going to be 10e to the 4th. Then if I take the log of these two values, so I have so let me run this for you. Control Enter. So there's F0, F1. I take the log of that. You see that's 0, right? So 10 to the 0 power is 1, and 5. So the log of 10e4 is 5. So now if I go from log 0 to log 1 by 0.1, you see I get this list of frequencies. And this list of frequencies, this is their logs, right? So they're linear. But let's look at the actual frequencies. And so if I look at the frequencies, you see this curve, because these will be, if I plot them in, let's plot them in log space. Okay, so let's do a semi-log. Let's do a figure, comma, semi-log x of control V. Well, that didn't work. Let me do a semi-log y then. There you go. And let's do it, comma, quote, dot, quote. There you go. Okay, so there you can see. So when I plot these guys out in log space, they're going to be linear points. And that's what you want. And so now, let's just do the, because I think I probably need to do this one. So I calculate the frequencies and then calculate the gain. So this is where you're going to put in your new equation on line 88. And then I'm going to plot the bodyplot, and there it is. Okay, so that's the same thing you had before. Let me plot this as comma quote dot quote. Let's do an O. Plot that again. There you go. So there you can see that the even though this is a log scale, you can see that the frequencies are spaced evenly. All right. So what you will need to do for your homework is to start here where on line 78. So I would copy all that, and then I would paste that into a new M file. And let me see, here we go. So which is going to be called bodeplot homework. And so here is the transfer function, whereas here I had 1 over tau s minus 1, or tau s plus 1. You're going to have 4,000 times the quantity 5 plus s, or if you use s, you can use s5 if you like, 10 plus s and divided by 100 plus s. And again, each of these is going to be term, and this one's going to be squared, right? So this is going to have to be a dot square, and this is going to have to be a dot divide and a dot divide. So I don't think that'll be too tough for you. And as a matter of fact, I can probably run that for you and let you look and see what it looks like here. And if I do that, don't know where it went. Hang on a second here. And there we go. That's what the that's what your bodyplot will look like. All right. Well, enjoy. All right. So this is what your bodyplot's going to look like.